It's a special pleasure to be speaking here in Göttingen. It's actually the second time I've been here. I first came in 1987, 27 years ago, when I was a 21-year-old student hitchhiking around Europe. I was on my way from Australia to study mathematics at Oxford. And I was in Germany, and I need to make a special trip to Göttingen to make a pilgrimage to the mathematics department at Göttingen, about which I had heard so much. Göttingen was the home of Gauss and Riemann and Klein, Hilbert, and Courant, and Noether, and Dirichlet, and on the list goes. A wonderful, wonderful place for mathematics. So I just snuck in to the mathematics department in the middle of the day, just to see all the pictures on the wall and the statues. I still have the photographs. Of course, Göttingen has been a wonderful place for physics as well, with many of the pioneers in quantum mechanics making their home here. Because of this connection, it was irresistible for me to talk about this topic in the foundations of physics today. Really what I will be speaking about is a topic at the intersection of the philosophy of physics, on the one hand, the foundations of quantum mechanics, and the philosophy of mind, on the other hand, the metaphysics of consciousness. These have often come together over the years in the idea that consciousness might play some role in quantum mechanics, perhaps in collapsing the quantum mechanical wave function. And it's that idea that I want to explore here. I should say that this work is joint work with a student of mine at the ANU who recently got his PhD in the philosophy of physics, Kelvin McQueen, and is working very much on these issues. Okay, so there's really two questions that simultaneously drive this talk. First, what is the place of consciousness in nature and in the physical world? Second, what is the reality behind quantum mechanics? I think these are two of the deepest philosophical questions in the world. That you might even make a case for them being the two hardest metaphysical questions in the world in making sense of reality. And there turn out to be all kinds of interesting potential links between the two. Consciousness. So by consciousness, I mean subjective experience. What it feels like to be a conscious being. My experiences of colors and shapes and sounds, of emotions and thoughts. Everything which feels like something from the first person point of view, this is part of consciousness, as I understand it. From the point of view of science, it looks like we're giant robots or computers that produce certain behavior. The behavior looks straightforward in principle to explain in physical terms, one might think. But there's a giant mystery about how one can explain consciousness in physical terms. And in other work, including some of the work that Simon talked about, I've argued that in fact one can't fully explain consciousness in terms of standard physical explanations, such as the explanations given by neuroscience and so on. These methods of neuroscience are very well suited for explaining behavior and functioning. These are what I sometimes call the easy problems of consciousness, but they always leave a gap to explaining consciousness. Why should all that functioning be accompanied by some associated subjective experience? I'm not going to rehearse those arguments today. Instead, I will take them in the background. There's some reason to think consciousness can't be explained in simple physical terms. The question then is, where does one go? If consciousness can't be explained in physical terms, looks like it's in some sense non-physical, and we need to expand our fundamental ontology to bring consciousness into the picture. So I've suggested that just as Maxwell went beyond space and time and mass. We couldn't explain electromagnetism in terms of those existing fundamentals, so we added charge as a new fundamental and new fundamental laws, likewise in the case of consciousness. But this then immediately raises an issue. What is the role, the causal role of consciousness in the physical world? What difference does it make? Many people have suggested that the domain of physics is completely closed. There's no room for consciousness to make a difference in the physical world. If that's right, it looks like consciousness must stand outside physics, epiphenomenal, as some people put it, making no difference, which is very strange because it seems that consciousness makes a big difference in our lives. So that's the first question. How can consciousness play a causal role? Here I have a little picture. Here's a depiction of the closest thing I could find on the web to depicting a brain and a non-physical consciousness, and then the question is, what on earth is the relationship between these two? How does consciousness play a role in guiding the brain and guiding behavior consistent with our scientific view of the world? Okay, so that's one question. The other question is, what's the reality behind quantum mechanics? Quantum mechanics postulates a wave-like reality, where things don't have definite properties at the bottom level. Instead, they're giant superpositions. But we experience a world with definite properties. How can we explain the relationship between the quantum mechanical reality and the classical reality we experience? Here's a little depiction of this. There's quantum mechanical reality, a whole bunch of waves and wave function described by the Schrödinger equation, which, if you look carefully, gets misspelled up there. Turns out that what you get from Google image search is not completely reliable. And somehow this wave function produces and otherwise this classical world we experience. Houses and trees and everything having definite properties. How does this happen? Well, one idea, which has been central in the foundations of quantum mechanics, is thinking that somehow there is a collapse from the superposed wave-like reality to a determinate reality, so-called collapse of the wave function. But as we'll see, that collapse raises many mysteries. But many people have supposed there is some link between those two questions. That the collapse of the wave function is somehow brought on by consciousness. You can see that if this was true, it would simultaneously address both of these questions. The transition from quantum mechanical reality to classical reality, and it would also give us a role for consciousness in the physical world, in affecting the quantum wave function. So it's a very attractive idea for that reason. At the same time, it's an idea that has not been taken very seriously in recent years. It has something of a bad reputation, I think, although it was introduced by some very serious physicists. In the 1970s, this view became associated with works like the Tao of Physics and the Dancing Mouli Masters, which tried to read in all kinds of Eastern ideas into physics, and it was not developed in a very rigorous and precise way. And most theorists have tended to set it aside. What we try to do here is to take that idea that consciousness collapses the wave function and at least formulate it in a rigorous and precise enough way that we can see what the merits of this theory might be and what the problems might be. I don't know whether the theory works. As you'll see towards the end, we may have succeeded a bit too well with making the theory precise enough to be refutable. It may end up being that it's been made precise enough that it is in fact refuted by some considerations. But I at least want to get these ideas onto the table so people can think about this class of theories in a rigorous and precise way. Okay, so I will start by explaining some background in quantum mechanics. How many people here already know something about quantum mechanics? About half. How many people don't? Okay, well, at least there's a fair amount of background, but I'll try to provide some very basic background of quantum mechanics, and you will not need anything technical to understand what follows. So just a couple of basic ideas. In classical physics, systems are described by definite values. A particle's position is specified by a definite location. In quantum mechanics, on the other hand, systems are described by wave functions. A particle's position is specified by a wave function with different amplitudes for different locations. So here's a rough depiction. Here's a classical particle represented by the red dot, classical harmonic oscillator. In every case, this particle has a definite position. Here's a quantum harmonic oscillator. There's a particle here. At any given time, the particle it's not specified by a definite location. Instead, there's a wave specification of its locations. The wave is in effect spread out over different locations with different amplitudes at the different locations. And that's the difference in the basic ontology of classical and quantum physics. Sometimes the wave function will specify a highly definite position with all the amplitude at one position, or at least localized around a single position. But very often, it will specify multiple positions with non-zero amplitude at many different positions. Then we say the particle is in a superposition of different positions. So in these cases, the particle is in a superposition of many different positions. Okay, so then we have the Schrödinger equation. Many apologies for leaving out the umlaut. Shouldn't do that here in Germany. The wave function usually evolves according to the Schrödinger equation. It doesn't matter for present purposes what the equation is. There's one mathematical representation of it. It's just a linear differential equation. Systems that start in definite states tend to evolve into superpositions. Start with a highly focused wave, spreads out, it gradually spreads out most of the time, according to the Schrödinger equation. Okay, so that's the core of quantum mechanics, is that differential equation, the Schrödinger equation for evolution of the wave function. But then there's special proviso about measurement. And this is what generates many of the mysteries. When one measures a quantity, such as position, one always observes a definite result. One doesn't see a superposition of results. When the system starts in a superposition of values, the measurement might reveal any of those individual values probabilistically. And there's a rule for determining those probabilities, named after Max Born, the great physicist, who of course was here at Göttingen for many years. There's also a connection between Max Born and Australia. He is the grandfather of the great Australian physicist Olivia Newton-John, who may be known to some of you. Not as many people maybe these days as in the old days. Remember the movie Grease? The song Let's Get Physical? It was a tribute to her grandfather, Max Born. Let's do physics. According to the Born rule, if one measures position, the probability of finding that the particle at that position is given by the Born rule. The details don't matter, it's just really a matter of taking the amplitude, squaring it, and taking the absolute value. The probability depends on the wave function's amplitude at that position. That's all you need to know. But so here's a simple representation of a wave function. A particle has a wave function, different amplitudes at different positions. It's most likely if you make a measurement, the particle is most likely to be found where the amplitude is high, but there's some probability it will be found where the amplitude is low, and the Born rule specifies the details. Okay, furthermore, so that tells you the probabilities for getting a certain result of measurement. But importantly, in the standard formalism, after measurement, the wave function enters a new state corresponding to the measurement result. It's initially in a superposition of positions. You make a measurement, you find a definite position. After the measurement, the wave function is in a new state with all the amplitude concentrated on that position. It's an eigenstate of the corresponding measurement operator. That process is often called collapse. So initially we have a wave function like this over many different positions. You make a measurement. Probabilistically, you find a certain definite value. Afterwards, the wave function is in a completely different state, localized around that position. And this process is often called collapse of the wave function, because it's collapsed from this big superposition to a relatively definite value. Okay, so something like this story is very much a standard formalism for predicting measurement results in quantum mechanics. I mean, of course, there are many different formalisms and many different ways of formalizing quantum mechanics, but something like this is pretty standard. But it's just as it stands, it's just a formalism for predicting measurement results, and it's a very successful formalism that provides very good probabilistic predictions. But it obviously raises many questions about what's really going on in reality. Behind this formalism, how could the universe be such that this formalism would be as successful as it is in making predictions? And this is what's turned into one of the deepest, I think, philosophical problems. And it's a genuinely new philosophical problem. It did not exist before about a century ago, when quantum mechanics was discovered, and now it's one of the hardest philosophical problems there is. The basic problem is what's known as the measurement problem. The formalism says collapse, this special process, takes place on measurement. But measurement is a highly imprecise and anthropocentric notion on the face of it. What on earth is measurement? When does measurement occur? How on earth could something like measurement play a role in fundamental physics? Measurement seems like this very high-level, vague notion, not the kind of thing that ought to play a role in the fundamental physics of the world. So answering those questions is the measurement problem. Because there's there's many different ways of understanding quantum mechanics depending on how you understand measurement, and as such it leaves many questions unanswered. There's the famous case, for example, of Schrödinger's cat. You have some radium atom which may decay with a certain probability. According to standard quantum mechanics, it will go into a superposition of decaying or not decaying. Furthermore, this atom is connected to an apparatus. If it decays, a certain lever might drop. That will cause the axe to drop, which will cause a beaker to release some poisonous liquid, which will give off some poisonous gas. If the gas is released, a cat will die. So if the atom decays, the cat will die. If the atom doesn't decay, the cat will live. Now, according to standard quantum mechanics, when a superposed system affects another system, you get an entangled superposition, where, for example, the position of the atom becomes entangled with the position of the molecule downstream, so they're both in a superposition. In principle, the lever could be in a superposition, the axe could be in a superposition, the beaker could be in a superposition, and even the cat could be in a superposition. The famous idea that maybe the cat is in a superposition of being both alive and dead before somebody looks at it. Now you might say, surely that's crazy, that couldn't follow. But then the challenge is to say where in this chain the system goes from being in a superposition to being in a definite value. Does the cat collapse the wave function? Does the beaker collapse the wave function? Does the axe? Does the lever? Do cells? Do molecules? Somewhere in this chain, either you say the cat is in a superposition of being alive or dead, or you say somewhere along this chain a measurement occurred and the wave function collapsed. But it's totally unclear from the standard formalism where this happens and what the criterion is. Is it levers? Is it molecules? We just don't know the answer to that question. And of course, there's the classic idea that it's in fact the observer who collapses the wave function. The cat itself is in a superposed state until a conscious observer comes along and takes a look. The cat goes from being both alive and dead to being alive or being dead. Of course, if the cat was conscious, you might think, well, the cat will then collapse the wave function itself. So I suppose we can imagine for the sake of our argument that the cat is under a general anesthetic, not conscious at all. Anyway, this is one classic idea. It's not forced on you, but it does bring out the importance of getting clear on what the measurement process is. In fact, we did the experiment in this case, and fortunately came out with a positive result. The cat might be forgiven some strong language given the trauma it's recently been through. So one needed. There are alternatives to quantum mechanics. Thanks. There are alternatives to the collapse alternative interpretation of quantum mechanics. And I won't be discussing them very much today. Many physicists and many philosophers have thought very hard about how the world could be so that wave functions don't have to collapse as they seem to in the standard formalism. There are approaches where there are hidden variables, so the particles have definite positions all along. David Bohm was a proponent of these theories. There are approaches where even macroscopic systems go into superpositions. Cats are both alive and dead. People might go into superpositions. Maybe there's a superposed wave function, one where I'm standing over here and one where I'm standing over here. In effect, the world evolves into different branches. That's often called the many worlds interpretation, associated with Hugh Everett. There are theories that try to retain the idea of collapse, but take away the idea of measurement playing a central role where collapses happen spontaneously or randomly. So the Girardi, Rimini, Weber, or GRW interpretation tries to formalize this. There are also interpretations that give a central role to decoherence, where the Schrödinger equation alone predicts that the wave function will resolve itself into several quasi-classical worlds. The trouble with that one is it looks like it has to be combined with something like the many worlds idea or the collapse idea to get further, to narrow things down to the world we see. In any case, I'm not going to be talking, all of these interpretations have virtues, all have problems. I'm not going to be talking about those interpretations today. As Dr. Friedrich mentioned in my first book, I tried to develop a version of the many worlds theory in context of a theory of consciousness. Today, I'm taking a different approach. I want to look at face value interpretations of quantum mechanics. Interpretations where collapses really do happen in reality. There's a real process of wave function collapse that happens in reality, triggered by measurement events. And it really does happen upon measurement. So this is taking that standard formalism of quantum mechanics at face value and trying to make sense of it. What one really needs to do to make this work is to make the notion of measurement precise, to precify it, as philosophers say, and then to clarify the basic principles by which measurement and collapse work. And I'm going to adopt a certain framework for doing that today. Again, I don't know whether this is correct, but I think it's at least worth trying to make precise so we can explore it. There's really two broad options here in understanding measurement. The first idea, which I'm eventually going to focus on, is that measurement is observation by consciousness. Measurement is what happens when a process affects a conscious observer, someone with subjective experience, and that consciousness somehow triggers the collapse. That's an idea that I'll get to. But I should note, though, that the framework I'm developing here doesn't require consciousness to play a central role. We could also suppose that measurement is just another physical process, but involving some special kind of physical process or physical property, and that somehow a certain special physical process triggers collapse. And so I'll initially start by developing this framework neutrally between the two. But here's the idea that I want to explore. There are certain special properties in the world. Call them M properties, or maybe M quantities, or in the quantum mechanical jargon, M observables. Ones which behave in a really distinctive way, and are subject to a distinctive fundamental law. The fundamental principle is that unlike other properties in quantum mechanics, M properties can never be superposed. They never enter into superposition. It's just the law of the system that M properties never enter into superpositions. Or a little bit more formally, a system's wave function is constrained so that it's always in an eigenstate of the M operator. That's an operator that corresponds to the M property. And that's going to be a constraint on Schrödinger evolution, which is going to introduce a different kind of dynamics. Roughly, the idea is the following. Whenever an M property enters a superposition, it collapses to definiteness. So just say position was an M property. Then whenever you've got a superposition of positions, it would immediately collapse with probabilities given by the Born rule for the associated M operator. In fact, on this system, on this framework, the property will never enter a superposition. Whenever it's about to enter a superposition, it will collapse to definiteness. And you can get the mathematics of this by just taking the limit of what would happen if suppose it collapsed after 1 second of superposition, suppose it collapsed after half a second of superposition, suppose it collapsed after a quarter of a second, and so on. Take that limit, and you'll get certain probabilities, and those will be the probabilities for collapse. One could, in principle, take any property to be an M property. Is in fact, different choices of M properties will yield different interpretations. This framework, in principle, yields an infinite number of interpretations of quantum mechanics depending on your choice of M property. And of course, I'm eventually going to suggest that consciousness might play that role. But before we get there, there's many other choices you might take. To illustrate, and this is just a fanciful idea for the purposes of illustration, not to be taken too seriously, let's suppose that M properties are positions, but positions of certain special particles. Call them the M particles. If you like, you can think of the M particle as a special, unusually, fairly rare fundamental particle. Maybe we can suppose that the Higgs boson is an M particle. I mean, there's all kinds of reasons why this won't work empirically, but we can just pretend. Or it could be some complex molecule, even. And then it's just going to be a law that M particles always have definite positions. That will be playing the role of a fundamental law. M particles are unusual in that they always have definite positions. The dynamics of M properties are going to be given. There's a fairly standard mathematics, a mathematics of continuous strong measurement of M quantities. It's exactly as if somebody external to the system was constantly measuring the M quantities. We can imagine, for example, that God is out there externally observing the physical universe and constantly measuring the M properties, the positions of all the M particles. As a result, they always collapse onto definite positions, and they never evolve anywhere. Now, we just take all that picture and subtract God. And that's the picture we have here. We don't require the notion of measurement here anymore. We don't require an external observer, but it's as if we applied the standard formalism to an external observer measuring M quantities. Now, okay, so how does this end up collapsing wave functions more generally? Well, the idea is that whenever some property is in a superposition, whenever that affects a system with an M property, it will become entangled with that M property. The M property will collapse, so the original property will collapse. So here's a quantum entanglement. It's just one particle affecting another. Let's pretend that one of them is just a regular particle, a photon. One of them is an M property. Sorry, an M particle. The photon is in a superposition of positions. It affects the M particle, so that normally the M particles would go into a superposition of positions by standard quantum mechanics. That's a quantum mechanical entanglement. But M particles cannot enter superpositions by our fundamental law. So if the photon with superposed position interacts with an M particle, the M particle will probabilistically collapse to a definite position. And so will the photon by the standard mathematics of entanglement. You basically have a mathematics of something like this, extremely simplified. The photon is initially in a superposition of two positions. Let's call it P1 plus P2. The M particle is in location M. Now the photon then has some interaction with the M particle, so that if the photon was in P1, the M particle would go to location M1. If the photon's in position P2, the M particle goes into location M2. By linearity of the Schrodinger equation, you get an entangled state resulting, basically, a superposition of the photon being in P1 and the M particle being in M1, the photon in P2, the M particle in M2. The M particle, in effect, but now that's a superposition involving M properties, and by our fundamental law, that cannot happen. So the M particle will collapse probabilistically onto M1 or M2. And the result will either be P1M1 or P2M2. In effect, the photon will collapse too. Collapsing the M property, the M particle collapses the position of the photon. In effect, the M particle is acting as a measuring instrument. If, for example, an M particle was in a single slit of the double slit experiment, and the photon goes through it, where you normally, without the M particle, you have a superposition of a photon going through both slits. Well, if the M particle is there, then that would normally lead to a superposition of the M particle being affected or not being affected. That can't happen. So it will collapse the position of a superposed photon to going through one slit or the other. I like to think of these M particles. I mean, of course, the M really stands for measurement, but you can think of the M particle as something like a Medusa particle. Remember the Medusa, everything that looks at the Medusa turns to stone. Well, this particle is such that everything it looks at turns to stone. Superpositions turn into definiteness. Or if you like, you can think of it as a Midas particle. Remember King Midas? Everything he touched turns to gold. Well, everything the M particle touches turns to definiteness, turns to collapse. Now, there are obvious constraints on what kind of thing could be an M particle. It can't be, for example, that photons are M particles, because we know that photons enter superpositions. You can send photons through two slits in a double slit experiment, and you get a certain interference pattern that results. This indicative and reflects the photon having associated uncollapsed wave function. If photons were M particles, that couldn't happen. M particles need to be rare enough that superpositions can persist, yielding the interference effects that we see. At the same time, they can't be too rare. if there are only M particles on Alpha Centauri and none anywhere on Earth, then they're going to be pretty useless for explaining the definite results that we get of measurements. When we make measurements, we get definite results. And it better turn out that M particles are at least always found in macroscopic systems, or at least in brains, so that when we make measurements, we always get definite results. If not, then our brains would just enter uncollapsed states, superpositions, and we'd be in a superposed measurement state where we didn't get definite results for our measurements at all, and then you either got a conflict with data, or you'd have to go down the path of the many worlds interpretation. So it's got to be intermediate. It's got to be intermediate in rarity. Okay, so I don't think the M particle idea is a serious one. But there are a lot of other candidates for M properties besides positions of M particles. There are all kinds of properties of simple and complex systems. They'll be subject to the same constraints. They have to be rare enough that observed interference effects don't involve M properties. That's enough to rule out, say, position, quite generally, or mass as M properties, because we do get superpositions of those properties. It's also enough to rule out certain complex properties of molecules like bacmethylfluorine, the famous buckyball molecule, which contains 60 carbon atoms arranged in a certain pattern. People have done experiments with these buckyballs showing that these produce interference results somewhat analogous to what you get with photons in a double slit experiment. That suggests that, okay, these things are actually entering superposed states. So it's not the case that the shape property of a buckyball collapses the wave function. It's got to be something more complicated than that, it seems. So that rules out some properties, but M properties have to be common enough that measurements always involve M properties. So it better be, again, that M properties are always at least present in brains. So some candidates for M properties. I mean, you might start looking at configurational properties of complex systems, like certain molecular shapes. Maybe certain shape properties can never be superposed. I mean, there's an idea out there which is that spatiotemporal properties serve as an M property. There's a theory of semi-classical gravity where space-time can never be superposed, or there's the related ideas of Roger Penrose where whenever space-time gets too superposed, it collapses again. Then the very structure of space-time is serving as an M property. Maybe molecular energy could serve as an M property. One interesting candidate is the property that Giulio Tononi has called phi. This is an information processing property. It measures the amount of information integration in a network. And there's a complicated mathematical equation for it. It's a complex system property. Tononi has argued that this property is actually a neural correlate, a physical correlate of consciousness. The more phi you have, the more consciousness you have. But for present purposes, we can just look at phi and suppose that phi might be an M property. And then whenever you get a superposition of phi, you'd collapse, thereby collapsing the wave function. Finally, there's the thought that M properties themselves might be mental properties, like consciousness. Consciousness itself could serve as an M property. And that's the hypothesis I want to develop in the next part of the talk, in the time that remains. It's worth noting, though, that different hypotheses about M properties yield different empirical predictions. I mean, basically, you could do what people think of as interferometer experiments, where you try to prepare a system so that it's in a superposition of M properties and see if interference effects result. So we do that with photons and position in a double slit experiment, and we get an interference wave arising from the wave-like nature of the photon that suggests that that property is in fact superposed. And you can do that for other particles. You can do it for electrons, you can do it for protons. But as the systems get bigger and more complex, it gets harder and harder to do these experiments. So far, people have done this for these 60 atom molecules, bacmethylfluorine. I gather people have moved it up about an order of magnitude beyond that, but not much further than that. It's very difficult to do these experiments because you have to prepare the system in complete isolation from its environment in a way that's very hard to do. But it is in principle possible to do these experiments that will distinguish the hypothesis that photons collapse the wave function, electrons collapse the wave function, buckyballs collapse the wave function, phi collapses the wave function. All of them give different empirical results in principle, although it's hard to test in practice. That's nice because it actually makes these frameworks all empirically distinct. It's also nice that it's not totally straightforward to establish or refute, because I'm in a nice position where the theory is empirically testable and refutable, but not so quickly that it's going to be tested and refuted tomorrow. Now there are many objections you might make to this from a physics standpoint. Because time is short, maybe I'll skip over them. There are worries about conservation of energy, serious worries about compatibility with relativity, as for most interpretations of quantum mechanics, worries about long tails. I think the most serious worry is tied to the quantum Zeno effect. This is the worry that probably ends up sinking the whole framework, but I'll come back to that at the end. There's also a worry about whether M properties, whether these high-level properties, really can play the role of entering into fundamental laws in the theory. But maybe I'll let people raise these in discussion and go on to consciousness. Okay, so the idea that consciousness plays a special role in collapsing the wave function is one with a quite illustrious history in the history of quantum mechanics. In von Neumann's original textbook on the mathematical foundations of quantum mechanics, he seems to suggest a version of this idea with a role for consciousness. London and Bauer did it in the famous paper in 1939. Wigner, who of course spent a portion of his career here in Göttingen, is perhaps most famously associated with this idea in an article on quantum mechanics and the mind-body problem in 1961, suggesting an explicit role for consciousness, though without really making it precise. Most recently, Henry Stapp has been a real pursuer of this idea, but I think in most of the developments it's never really been made fully rigorous and precise. And, Wigner's treatment is informal, Stapp's theory is somewhat formal, but has some key obscurities at its heart. So I think it's really never been made rigorous. I'm not going to claim that what I'm saying here today is totally rigorous either. I think it at least moves in the direction of making the ideas precise and subject to rigorous argument. The hypothesis in the current framework is that consciousness is an M property. Consciousness can never be superposed. You've got different states of consciousness, like seeing red and seeing green, or feeling pain or feeling fine. And the claim is that consciousness can never be superposed. You can't have two states of consciousness at once in a superposition. Whenever consciousness is about to enter a superposition, the wave function collapses, just as for other M properties before. So take a superposed electron. It's in a superposition of positions, S1 and S2. We consciously perceive it, potentially yielding a superposition, which I'll represent as S1, with me consciously perceiving the electron to be in S1, that's one measurement result, and S2, with me consciously perceiving the electron to be in S2. One of them I see a pointer here, and the other one I see a pointer there. And the claim is that, okay, consciousness cannot superpose. So consciousness must collapse probabilistically to one of these states, say C of S1. So you get the electron collapses, consciousness collapses to C of S1, the electron collapses to S1, the result is a definite state. Electron in S1, and me being conscious of the electron in S1. So in effect, consciousness collapses the electron's wave function. Now, consciousness, I just said there's any number of choices, potential choices of M properties. Consciousness is just one potential choice among many, and I don't claim it's forced on one by the framework or by the data. But taking consciousness as an M property does have a number of theoretical virtues. I've listed them here in order of strength, probably from weakest to strongest reasons. First of all, there's a conceptual virtue. It offers a very natural clarification of the idea of measurement. It's at least very natural to understand measurement as conscious perception or interaction with a conscious agent. Not the only way to go, but one very natural way to go. Second is an epistemological virtue, saving the data of observation. Arguably, the central data that's posing the measurement problem is that we always, when we make a measurement, we always get definite results. And the datum here is when we make a conscious measurement, we always get a definite result. Nobody ever sees a superposition. That's arguably a datum without consciousness. This theory is perfectly suited to save that datum. Maybe other theories might if they postulated something closely related enough to consciousness, but this is more or less guaranteed to do it. Third, there's a potential explanatory virtue. You might argue that consciousness has the special advantage of potentially explaining where this non-superposability constraint comes from. But you might take it that it's in the very nature of consciousness that it can't be superposed. I mean, it's arguable that one can't even imagine a superposition of consciousness. What would it be to be simultaneously perceiving red on location and perceiving green, not as elements of a single conscious state, but as a superposition? I think one can at least argue that that is both inconceivable and somehow impossible by the very nature of consciousness. If that was right, something about the nature of consciousness might explain this non-superposability constraint and make that fundamental principle that M properties can't be superposed somehow more intelligible and more transparent. I don't know that constraint is not obvious, but I think it's at least an attractive place to look. A metaphysical virtue is that this collapse principle, this non-superposability principle, will on this framework be a fundamental law of the theory. And you might think that fundamental laws want to have fundamental properties entering into them. On the other views, we have high-level properties like molecular shape or phi entering into this law. On this approach, if you take consciousness itself to be a fundamental property, as at least I do, then you've got the virtue that a fundamental property is entering the law. Fifth, and perhaps most important, this has the virtue of finding a physical role for consciousness. One of the biggest problems that we have in trying to make sense of nature. If indeed consciousness is somehow something over and above standard physics, what role does it play? Because it sure seems to play a role. Here we can actually find that role. So anyway, these are 5 reasons to at least take the view seriously. I should note that everything I've said so far is consistent with both physicalism and with dualism. You could take consciousness to be an M property and identify consciousness with some complex physical property. You won't then get all the virtues on the previous slide. You'll have some non-fundamental property collapsing wave functions. Still, you can still take on board much of the rest of it. But it's also consistent with dualism. And here at dualism, I just basically understand to be the view that consciousness is a fundamental property distinct from all the other fundamental properties in nature, like space and time and mass and charge, the ones postulated by standard physics. You can take it that consciousness is fundamental and non-physical, and this is in fact the fundamental law that it enters into, connecting it to the rest of physics. And maybe the view is especially well motivated on that view because it finds a role for that fundamental property, something about which we were otherwise worried. I should note that it's not consistent with the metaphysical view of panpsychism, that consciousness is everywhere, that every system, even photons, are conscious. Because, photons are conscious, and consciousness always collapses the wave function, and photons will always collapse the wave function. But we know that doesn't happen. Photons enter into superpositions, and photons enter into superpositions. And likewise for the other properties. Now, there's this interesting sociological phenomenon that, philosophers often reject dualism precisely on the grounds. The biggest problem for dualism is often held to be the interaction problem. Physics is causally closed. So there's no role for non-physical consciousness to make a difference in the physical world. If you think about all this, it's arguable at least that physics leaves a giant causal opening for consciousness in the collapse process. If you look at the standard formalism of quantum mechanics, it's like constant evolution according to the Schrödinger equation, and then occasional jumps, collapse, jumps, collapse. Jumps, openings that seem to be oddly associated with agents and measurements and so on. I don't say that forces a role for consciousness on you, but it does seem to be a giant causal opening that's perfectly suited for consciousness to fill. In fact, there's this odd situation. Physicists. I take it there are some physicists in the audience today. Physicists will often look at this framework, the whole consciousness collapse framework, and say, well, this is kind of crazy, or we should reject it because it's dualistic. It's postulating consciousness as a fundamental property. Why should we believe that? That's not physics, and so on. I'd say that's the single most common reason for rejecting consciousness collapse interpretations. At the same time, philosophers often reject dualism because they take it to be incompatible with physics. Physics is causally closed, there's no room for consciousness. This is an odd situation. Physicists reject collapse because of philosophy. Philosophers reject dualism because of physics. And if you think about it, you put those, and those are probably the two biggest reasons. That's the single biggest objection to consciousness collapse interpretations and to dualism. I think if those are your only reasons for rejecting the two, then collectively they have zero force. No force at all. What is true is if there are some further reasons for rejecting dualism, or some further reasons for rejecting collapse, then that might spiral into reasons for rejecting both. But at the very least, independent reasons for rejection seem to be needed. These two objections, the single biggest objections to each theory, don't seem to collectively carry much weight on their own. Now, what are the laws going to look like on this view? We'll have the standard Schrödinger equation and standard physical laws. Then we'll also have consciousness as a fundamental property involved in fundamental psychophysical laws. Now, standardly, for a dualist thinking about consciousness, there's two different ways to think about those laws. You have unidirectional laws, just from physics to consciousness, but not back again. That leads to the position of epiphenomenalism. Physics makes a difference to consciousness doesn't make any difference to physics and physical processes, often regarded as counterintuitive. Or there's interactionism with bidirectional laws. Physics to consciousness back to physics. I hope it's clear that the view I've been developing here is a version of interactionism. In the past, I focused a lot on developing views that look more like epiphenomenalism or panpsychism, but you can see this as at least the beginnings of a flirtation with interactionism to see if we can make sense of that kind of framework. In effect, we have a physics to consciousness law. Something like some physical quantity P yields consciousness. Maybe it's Tononi's phi, for example. High phi yields consciousness, and so on for specific kinds of consciousness. And we'll have a consciousness to physics law. Consciousness is never superposed, and it gets entangled with physical states in such a way that collapse of consciousness yields collapse of the physical states it's entangled with. So if consciousness is correlating with phi, for example, consciousness collapses, phi collapses. The neural correlates of consciousness collapse, and things go on in the physical world from there. Now, there's any number of objections you might raise at this point and worries. I'll just mention a few of them. One is the worry that unobserved macroscopic systems will be in superpositions until we measure them. So, Schrödinger's cat, for example, if anesthetized, might be in superposition until someone looks at it. Or these ordinary measuring devices, if they're isolated and they measure a quantum process and no one looks at them, then they'll be in superposition. The pointer will be in a superposition until someone looks. Well, two levels of response to that. One is, it's not obvious that's the case. That depends on the complexity of the property P that gives you consciousness. If it's a simple enough property, then these won't go into superpositions, they'll collapse. And macroscopic systems won't be. But on the other hand, we can also say, if it's a complex property, P, one that we only find in brains, then yes, it will turn out that ordinary measuring devices do enter into superpositions when no one looks. That is counterintuitive, but it doesn't contradict any observational evidence. It's merely a bit of weirdness in the world. We know quantum mechanics is weird, so be it. Another worry is that consciousness collapse will be empirically equivalent to a certain purely physical theory. The theory that P, the physical correlate of consciousness, is an M property. So just say high phi gives you consciousness, and consciousness collapses the wave function. Why not just say that high phi collapses the wave function? It's all physical. For those of you who think about the philosophy of this, philosophers sometimes talk about zombies and zombie worlds. which are physically identical to our world with no consciousness. You might say, isn't that true here? We have a world where all those wave functions do that collapsing without there being any consciousness at all. In effect, in that world, phi, the physical property, will do the collapsing. And I think it's true that these two theories will end up being empirically equivalent. Nonetheless, they're different theories. They postulate a different causal process. And on the consciousness collapse interpretation, it is fundamentally consciousness that's doing the causal work. And the argument is going to be that although these two theories are empirically indistinguishable, the consciousness collapse theories, especially if one takes into account the fact that we've already got independent reasons for believing in consciousness and for believing it's fundamental, then it turns out to have extra explanatory metaphysical and causal virtues, as outlined before. It might even be that this framework could suggest an empirical criterion for consciousness. Say we find empirically that property P is associated with collapse. That will then give us, perhaps non-conclusive reason, to accept that P is the physical correlate of consciousness. Especially if it turns out that P is independently plausible as a correlate, something found in brains, something like high phi, and so on. Then, in effect, interferometers and experiments like this might serve as the fabled consciousness meter, giving us a test for the presence of consciousness. There are worries about whether this is getting the right causal role for consciousness. Is it just collapsing? After all, we didn't just want consciousness to collapse things you see. We want it to make a difference to your action. Well, I think what's actually going to happen here when you think about it is that consciousness most directly interacts with the neural correlates of consciousness, collapsing those out of a superposition. So when you have an experience of red as opposed to green, that may collapse a superposition around the neural correlates of consciousness, say inferior temporal cortex, into the neural correlates of seeing red, as opposed to the neural correlates of seeing green. That will then have effects downstream. It'll cause behavioral reports like I'm seeing red. So that's the kind of causal effect on action that we want. You can also give a special role to collapses of agentive experience, like intending to do something or deciding to do something. Those may be especially directly connected to action. There's a worry here that consciousness is just rolling quantum dice. It's only playing a probabilistic role. It's not somehow making actions more and more intelligent. It yields probabilistic outcomes, the same as in quantum zombies. It doesn't make us more likely to behave intelligently or say, I'm conscious. I think that's true. But at least consciousness is in the loop, playing a role on this approach. Okay, the biggest worry, and I'll just mention this fairly briefly, is, as I alluded to already, the quantum Zeno effect, which really does threaten to sink this whole approach. The quantum Zeno effect basically says that frequent quantum measurement makes it hard for measured quantities to change. The more frequent you measure something, the harder it is for it to change in the limit. You measure something constantly, it won't change at all. So the worry is the continuous collapse of consciousness will make it very difficult for consciousness to evolve in the first place. The way you might think about it is in the initial state of the universe, you've got a giant Schrödinger superposition of many, many branches of the wave function, each of them with no consciousness. For the first time, a little bit of consciousness begins to evolve in one branch. A little bit of amplitude for the branch with consciousness. Well, that will trigger a collapse, because consciousness can't be superposed. But almost all the amplitude of the wave function is going to be in the no consciousness branch. So with enormously high probability, it will collapse back onto no consciousness. In fact, in a limit, with probability 1, it will collapse back onto no consciousness. In which case, we get probability 0 for consciousness evolving. Not a good result. You might also worry that this is going to make it very hard for you to have your consciousness wake up after a nap. If any of you are nodding off in the audience, be very, very careful, because it's going to turn out to be quite difficult for consciousness to come back in again. Maybe have somebody else there watching you and collapsing you back into wakefulness. There are various ideas for handling the quantum Zeno effect. Actually, my current suspicion is this sinks the whole approach, unfortunately. But there are various ways you might try to handle it. Add some new intra-consciousness dynamics to the system that would be more strongly dualistic. One idea very much worth pursuing is the idea of intermittent probabilistic collapse, analogous to that GRW idea, but now applied to M properties. So consciousness goes for a while into a superposition and then collapses. That might be closer to getting the right results. There's also an alternative approach where it's not consciousness directly that's collapsed, but the properties you're attending to in consciousness, or the properties you're representing in consciousness, like positions or colors. This will then have the property, the approach that, these properties can enter into superpositions for a while until someone attends to them, and then the wave function collapses. That's going to be quite a different approach, but one I think worth pursuing. Anyway, enough on this then. If all this can be made to work, and of course that's a very, very big if, then I think consciousness collapse interpretations promise simultaneously an attractive, empirically testable interpretation of quantum mechanics and an attractive approach to the mind-body problem, one that might finally offer some kind of place for irreducible minds in nature and a happy resolution to the tale of Schrödinger's cat. Thank you.
Thanks a lot for a very good lecture. It's now 7:30. Perhaps we can have 20 minutes of discussion. Okay. Raise your hand and I'll give you the microphone. You go first.
I'm not a physicist, so I don't understand how well your M-object theory or M-process theory explains the problems in collapsing the wave function. But if I replaced every occurrence of the word consciousness in your talk with the word measurement, would I effectively give exactly the same talk?
Yeah, I guess I would think no, because measurement is just a very ill-defined notion and very imprecise, whereas at least on my view, consciousness is well-defined and it is precise. Every system is in a very definite, very precise state of consciousness. There's something quite precise, it feels like, to be me right now, something quite precise it's like to be you.
But conscious percepts are not always so well defined. So if I have a very ill-defined percept of red, it comes down to whether from the output of the retina, if I measured all the spikes, a potential photon could have, there is internal noise and then there is may or may not have been a photon. So you just have a device out there that's eventually reflecting in a vague percent of maybe I saw the light, maybe I don't. 55% of the time I think there was a light and I was right. I never really saw a light in the first place. So eventually you have a measurement instrument with some noise, and now in this case effectively the cat is acting as a measuring instrument for that photon instead of the retina, and it is collapsing there. So I'm just wondering where consciousness comes into any of this.
So there's certainly a lot of noise in the perceptual process, but at least I should have said, this assumption behind this, the consciousness itself is always in a definite state. So maybe a given photon, there are things the retina might do that might lead me to have no conscious perception, to have only a very dim conscious perception, or to have a vivid conscious perception. And maybe my judgments will often be uncertain about whether I had a conscious perception or not. But I think it's independently plausible that consciousness itself is always in a definite state. If so, then that's one strong reason for going for consciousness over and above the others. The other reasons are tied to the things I suggested. There's some independent reason for thinking consciousness is fundamental.
I'll yield the mic now, but I would still hold that this is essentially untestable at some point.
Well, I think some parts of it at least are testable.
Okay, there was someone here. Was it you? Okay.
So my question regards the issue of attention in a sense. I mean, we have consciousness and we have consciousness attention to things. So how does this enter? So when does the consciousness property know that it observes something? If it's just basically the interaction in the sense of entanglement, could we then just do the search for extraterrestrial intelligence by, I don't know, having a large bomb or something correlated with a microwave signal which is transmitted to space? So as soon as something just picks up one of these photons, which is a conscious being, the thing would go off and we would know that there are conscious beings out there.
I have to get the details of the thought experiment. It sounds like a good one. But on the general point, you're right that the framework I've developed here gives no special role to attention. Basically, what triggers collapse is not attending to a property. Collapse is triggered whenever some property out there in the world has some effect on my consciousness. One way that can happen is by me attending to it. I look at the color. There's another way that can happen is by it's just, something happens in the background, has some little effect on the background of my consciousness. All you need is a differential effect on consciousness by the two states in a superposition, and that will suffice on this theory. Now, I didn't quite get enough about the bomb case.
So I mean, the question is, when is an interaction with a consciousness? So if a photon hits your retina, when would you say it? You consciously perceive it, and when not? Because, I mean, the thought experiment is if you make like a Schrödinger cat experiment, not with a cat, but with some microscopic bomb or something that we would see exploding. I mean, we must not attend to it, we must not measure the thing, but we must, get see the effects of the collapse of the wave function. Then we entangle some kind of radio frequency thing with the thing, send it out to space, probably start in a satellite so that we do not accidentally look at it. And then as soon as it would hit an alien, a conscious alien, then the thing would go, the wave function would collapse, the bomb would be triggered, and you would realize, there's aliens. Or there's other conscious beings.
It seems that for this to work, you're going to need some special mechanism which will the bomb will only go off if it interacts with a conscious being. What is that?
Isn't that the point? Is I have put the bomb in an entangled state with my radio signal.
Yeah.
And I make very sure that it's launched from some satellite that no human will observe it. So no conscious being, no conscious human being will observe that photons of the radio signal. So as soon as that thing hits some alien, some conscious being...
So the bomb is here on Earth.
Yeah.
And there's something...
I mean, on a bomb or a flag or something, so some device which we would see the collapse of the wave function as a macroscopic property that we would then see.
So the bomb is in an entangled state here on Earth. We send off a photon. Someone out there collapses the photon, and eventually
that's the
bomb goes off.
I just came up with it. Maybe it's not.
I mean, it seems to me that something like this we've got to get very similar results of many interpretations of quantum mechanics here, including spontaneous collapse theories. The bombs will go off at some point. On probabilistic theories, you're going to get I'm not sure you're going to get, as about food, I'm not sure you're going to get distinctive predictions from this approach, which I think is what you'd expect, because these different theories of quantum mechanics is close enough to being empirically indistinguishable. They're only distinguishable in very special circumstances. Maybe you could prepare a bomb in just the right way that would actually produce it. Anyway,
I should think about it. Probably write an email.
It's a great case. Thanks.
Hi. Thank you for the nice talk. Are you saying that consciousness is the only agent capable of causing quantum collapse?
On the interpretation I offered, the one where consciousness is an M property, yes.
Because there are many bacteria, for example, that need to transfer electrons from A to B. And so the position of the electron must be precise. So are you saying that bacteria must have consciousness?
No, I'm saying that bacteria could do that work even if they don't collapse the wave function. I think the mathematics will still go through perfectly fine even if bacteria do all this in a superposition. They'll just be in a superposition of branches, in all of which different positions get transmitted. It will be a version of the same way it works for molecules, like
I don't quite follow the argument, but...
Here is the place where the mathematics of decoherence really does become useful. You can represent the wave function. If there's enough decoherence in bacteria, you can represent the wave function as a superposition of different quasi-classical states, each of which behave roughly as you're mentioning, as you're suggesting. The claim is just going to be that before conscious observation, the bacterium is in a superposition of each of those quasi-classical states. Observation or interaction with a conscious observer will just play the role of selecting one of those quasi-classical states as the outcome.
Yes, thank you. I have a question also regarding, well, me trying to better understand what you're saying. If I have a simple physical process and some machine, which obviously has no consciousness, makes a measurement and writes down the result. Okay, this particle is in the right box or in the left box. Then you have your result, and like a year later I go and watch it for the first time. Is that the measurement only a year later, or has the measurement been done before? And part B of the same question, if two people go there independently, not talking to each other, when is the measurement done?
Yeah, I mean, it's going to depend on what the M properties are and which systems have them. But let's assume that the M property is conscious, and let's assume there's no consciousness in the measuring device. Then yes, on that framework, the measurement, the collapse will happen when a conscious observer looks at it. So for the first year, assuming there's no consciousness in the measuring device, it will be, and it doesn't interact with any consciousness, say it's sealed inside a lead box, then it will be in a superposition until a conscious observer comes along and selects one of the elements of that superposition as the reality. If there are two people, it's whoever gets there first.
So then the two people are entangled.
Well, I think it's going to depend on the case. They might be, but they needn't be. Two non-entangled people could come along and one will just, one person becomes entangled with the box, thereby collapses the wave function of the box to a definite state. Now it's just a quasi-classical system for all we might say. Another person will just come along and observe it without any special need for entanglement. There is a worry about conflict with relativity here, because we do need both collapses happen all at once, we need a notion of time ordering and so on, which is a big problem for any collapse theory.
Okay, other questions? You?
Yeah, I'm just still a little unclear on why consciousness is playing this special role as this having this M property. It seems to me that maybe God is this M property or something like that that you mentioned, and so I'm just not really grasping why we should think that consciousness gives us this M property over any other kind of explanation we might insert in there. So I can understand the elegance of the sort of thing coming together and how it explains so many things.
Well, I guess, so it was roughly these 5 virtues that I outlined. I should say this is much better motivated against the background of someone like me who thinks there are independent reasons for thinking consciousness can't be reductively explained in terms of things like particle interactions and standard physical properties. Because then the biggest objection to that view is consciousness must play a causal role in the world, surely. But where is the causal role for it to play? At the very least, this will then, against that background, give you the role of consciousness playing a causal role, and also the extra metaphysical virtue that what's playing that role in a fundamental law is itself a fundamental property, which is a big virtue. Now, someone who doesn't share that background with me, of course it's a controversial claim that consciousness is irreducible and fundamental, will have fewer motivations for the idea. Although I'd still like to think that those first 2 or 3 might serve as some motivation. But I don't claim that it's forced on you by the data.
Yeah, well, certainly it seems that there's a motivation, but it seems like there might also be a motivation to believe that the M property is God or something like that. It seems like there might be motivation there, but I guess so even if I'm willing to take on the philosophical baggage of dualism or something like that, I still, perhaps you're explaining it and it's just going over.
Remember, these theories do make different hypotheses about the M properties, do make different empirical predictions at the end of the day. I don't know how God is going to fit into this story, but I don't see exactly where that's going to... I mean, the thing that consciousness does, in the context of a specific theory of consciousness, is going to come up with certain specific empirical predictions and the hypothesis that something, that bottles collapse wave function. But why isn't it bottles that collapse wave function? Well, it's going to be a very inelegant, one, it'll be a very inelegant theory, but 2, we can in fact, will eventually be able to empirically test that theory and see whether they do it or not. So the empirical constraints, I think, also help here.
Okay. Max?
In experiments to unconscious processing when persons claim not to have seen curing stimuli, or not to have, but they behave above chance. The experiment results in above chance, but they claim not to have seen anything, but they're just guessing. Has then the wave function been collapsed?
Yeah, it's a great question. So what happens in cases of unconscious perception? And the actual experiments here are very controversial, and some people think that there's some conscious perception in the cases where people don't report anything. But let's suppose there is really true unconscious perception in those cases. And I guess I'd be inclined to say, well, in all the cases you're describing, people actually make a report and they make a judgment. So there's unconscious perception. I think what the consciousness collapse theory would say is that in fact the brain goes through a superposition at the level of unconscious processes, because it doesn't go through the neural correlate of consciousness. The rest of the brain is in a superposition until somewhere a bit causally downstream the subject comes to make a judgment. Where is it? And the subject judges it was there or it was there. And of course those judgments are at least somewhat accurate. They're entangled with the unconscious processes. Of course the judgment itself is conscious. So you'll always make a determinate judgment, and that will be collapsed. And then because that's entangled with the unconscious processes, at the moment of making the judgment, when it collapses onto a definite state, the unconscious processes will collapse too.
Thanks.
Okay, 2 more questions. And we can also close after that.
Thank you. My first question would be, was there a point in time where no consciousness was?
Yes.
Okay, so
On this view. The other half the time I'm a dualist, half the time I'm a panpsychist. When I'm a panpsychist, I'll say no, but I won't embrace this interpretation. When I'm a dualist, I'll say yes.
so in the history of biology, there was something like the first consciousness.
Yes.
Okay, so my question is, before this consciousness existed, there was like a crudely superposed nature, and then spontaneously consciousness begins to evolve. So my question is, how can a thing which has an end property, so its intrinsic property is that it's not superposable, how can that evolve spontaneously?
Well, I guess the way of thinking about this is there are worries about the evolution of consciousness, which I got to at the end, but the basic idea is we'll have some the way I'm thinking about it is there's some quasi-classical laws that say, there are psychophysical laws, say for example, certain values of phi give you consciousness. Once phi, Tononi's measure of information integration, crosses a certain threshold, you get consciousness. At the beginning, phi is below threshold throughout the universe. The universe is in just say the relevant property is when phi greater than 10. Well, the universe is in an eigenstate of that. It's less than 10 everywhere. At some point, in one of the branches of the wave function, phi creeps above that threshold. It creeps up to 10. Suddenly now, phi is in a superposition of being below 10 and being above 10. Or at least it would be in that superposition if that quality could be superposed. But since it can't be superposed, the moment it creeps above 10 in one of the branches, or the moment it's about to, then it collapses, either onto being below 10 everywhere or being above 10 everywhere. Likewise, if we work with consciousness as the end property, the moment you get a speck of consciousness, previously the universe was in an eigenstate of no consciousness. Now it's about to approach a superposition or a little bit of consciousness somewhere. The moment that happens, it has to collapse. And I raise the bar that it's going to collapse with probability 1 onto zero consciousness, which maybe one could try to solve by making the collapses more intermittent. But at least that's the rough mechanism.
So you would see the first consciousness as kind of a stochastic output of a random generator.
Yeah, I guess it will exactly. Think about it. The Schrödinger equation is certainly deterministic. That will be determined by initial conditions and deterministic evolution. But the moment there's a speck of consciousness somewhere, then the collapse will be probabilistic. And the hope might be with intermittent collapse. Well, maybe the first n dozen collapses will all collapse into no consciousness, but sometime with some probability, the universe will collapse onto the presence of consciousness. Some people have even suggested, I'm not sure if this works, something like this might actually serve as an explanation of why evolution has been so quick, against the background of it seeming improbable. Well, consciousness is very improbable, but once it happens, the universe will collapse onto it and will select that pathway. I mean, the way I've developed it, that will not be a consequence, but you can imagine versions of this framework that go that way.
Thank you.
So if the photon registers on the retina and a spike is elicited, but the subject does not perceive it, did the photon exist or not?
Okay, the photon registers on the retina.
And the spike is elicited from the ganglion cell, but the subject absolutely does not perceive it because of internal noise. Did that photon exist or not?
I would say absolutely it did, but it may well have been in a superposed state, and the unconscious processes it affected. If they have no effect on consciousness, they may well be superposed as well. The unconscious on this view, obviously the unconscious is even more complicated than Freud imagined. It's roiling set of your desires and so on. Your unconscious may be in a large superposition until it has some effect on consciousness. It probably actually happens quite often. The moment it has an effect on consciousness, all that will be collapsed. Insofar as it has no effect on consciousness, it may remain in a quantum superposition.
So the retina as a measurement instrument is superseded by the conscious report, effectively.
I would say that, in effect, for the retina the retina will go into definite states insofar as it has an effect on consciousness.
Thanks.
Superpositions are still pretty good measuring instruments. I mean, one superposition, a wave function can measure another wave function via causal connections, but it won't go into a definite state until there's an effect on consciousness.
Okay, then I think we close the discussion. Thanks again today for coming and giving this lecture. And I'm really glad that so many people came. Some of these people might join us at the restaurant, but only some. if you urgently want to continue discussing with Dave or anything. But please don't come all.
Make a roll the quantum dice, and maybe we'll get a superposition of people coming. The restaurant will collapse the group.
Thanks again.